To talk about some work we are doing on characterizing gelation in associating polymer solutions. And the work's been done by my student Aritra in collaboration with Gareth McKinley from MIT. So as you're all aware, associating polymers are polymers with attractive groups along their backbone, which can stick to each other. And so they can stick to each other within a chain, which are called intra-chain associations, or they could stick to each other in different chains, which are called interchain associations. And when the concentration is low, mainly most of the sticking goes on within a chain. There are intra-chain interactions. And as you increase the concentration of the polymer, you have more and more interchain associations forming, becoming micelles and clusters until you can have a system spanning network. So this point, when you have a network across the entire system, is denoted as the sol-gel transition, because you then have a gel phase. Now, what makes associative polymers so attractive is because you can really tune their properties by changing the number of stickers, the distance between their along the backbone, their strength, and so on, and the concentration of the solution, along with the temperature. And so you can get a fine control of its properties. And this has led to a number of applications in a large number of areas. And in particular, the gel phase has found application in many areas. So it's clear that characterizing gelation, what are the conditions that lead to its onset, what are the mechanisms that cause it on a molecular scale, all these are really important questions if we want to be able to rationally design associative polymer systems with a number of customizable properties. Right? So the aim of our work is to develop a simulation algorithm that will allow us to simulate the dynamics of associating polymer solutions and actually try to understand some of these underlying molecular phenomena. And also the collaboration with Gareth is with the hope that we can do carefully designed experiments to compare with our predictions. Now, in general, gelation is characterized typically by linear viscoelastic rheological measurement. So one could do a simple shear flow and measure the viscosity in the limit of zero shear rate, or one could do small amplitude oscillatory shear flow and measure the storage and loss moduli G prime and G double prime and their ratio tan delta. And the reason this is done is these functions show a characteristic behavior at the onset of gelation. And in fact, there seem to be two broad classes of behavior one can observe. Typically, what is observed is what we think is the so-called strong gel behavior, where the storage and loss modulus G prime and G double prime, rather than intersecting at some typical frequency, actually become parallel to each other across a range of frequencies. And as illustrated here in these very nice experiments by Lee and Aoki, it shows you G prime and G double prime becoming almost parallel to each other, and that particular concentration, the gelation concentration, tan delta, becomes independent of frequency, as shown here. And in fact, in some beautiful experiments done by Suman and Joshi, they observe a similar independence of frequency of tan delta as a function of temperature, which allows them to identify the critical gelation temperature. In fact, Suman and Joshi also observe that the viscosity and the relaxation time, both of them diverge as one approaches the gelation point. And this one expects as the sol becomes solidified and into a gel, right? On the other hand, in what we think may be the so-called weak gel characterization or behavior that is observed is that G prime and G double prime actually intersected each other rather than becoming parallel. And the viscosity is not observed to diverge. And in these experiments shown here by Bromberg, the viscosity actually seems to show a power law increase with concentration when it's measured as the concentration as distance from the gel point, right? Now, these weak gels, Indai and co-workers argue that it may be because the largest cluster relaxes before it breaks, and therefore the relaxation time doesn't diverge. To the best of our knowledge, we're not very sure if this distinction between weak and strong gels is widely recognized in literature. And so this is part of the problem that we want to address. What leads to the difference in this observed behavior between a weak gel and a strong gel? So if we were to develop a so-called to-do list for simulations, we would obviously need to put in all the microscopic physics that describes a polymer solution, such as excluded volume and hydrodynamic interactions. And we would have to be able to describe these behavior of stickers, how many there are along a backbone, and so on, and be able to vary their strength. And finally, we would vary these parameters and map out the concentration and temperature dependence of all these properties, right? So what we are going to do is work with a bead spring chain with stickers placed periodically along the backbone. And we're going to, because we are simulating systems at finite concentration, we're going to use periodic boundary conditions. And here's an image of a periodic simulation cell. And then the key element in our simulations is the potential that we use to describe the attraction between stickers, right? So rather than use the conventional Lennard-Jones potential, we're using something called the Soderman-Dunweg-Kramer potential. And this is essentially a modified Lennard-Jones potential where instead of the infinite range of the Lennard-Jones, there's a sharp cutoff at a finite value, and we can simply vary the attraction between stickers by changing this well depth. So it allows us to actually simulate both the backbone monomers and the sticker monomers with the same potential, right? And then we carry out Brownian dynamic simulations, which gives us the motion of every single bead in the system as a stochastic trajectory. Because we are accounting for hydrodynamic interactions, it leads to some complications because it's long range, which we've resolved by developing an optimized evolved algorithm, right? So once we have these stochastic trajectories, we can then carry out appropriate averages and calculate all the necessary properties. Now, we could, in trying to characterize gelation, do exactly what experimentalists do, that is to run a lot of finite shear rate simulations in shear flow and then find the viscosity and extrapolate to zero shear rate, and run several oscillatory shear flow simulations at different frequencies, and then plot G prime and G double prime as a function of frequency. Alternatively, because we are interested in a linear viscoelastic property, we could make use of the Green-Kubo relation that gives us the relaxation modulus G of t in terms of the stress autocorrelation function. And once you have the stress autocorrelation function, and these are just through equilibrium simulations, you can carry out an integral over time and find the zero shear rate viscosity, and similarly do a Fourier transform of the stress autocorrelation function to find both G prime and G double prime. Now, this expression that connects viscosity and the stress autocorrelation function is only true if G equilibrium is zero, and this is always true in a solution and in the solve phase, and obviously not true in a strong gel because of the viscosity diverges and if G equilibrium is non-zero, but if it's zero, then this is valid even in the gel phase. Okay, now while these are used to characterize dynamic signature of gelation, there are also static signatures of gelation. And interestingly, there is no clear kind of understanding of how does one characterize gelation statically. There seem to be three different ways of doing it. The first one says, what is the concentration at which you have a system spanning cluster when this first appears, or when does the probability distribution of chain cluster sizes first become bimodal? And finally, people also use the idea that the concentration of free chains, that is those that have no interchain interactions, when does this concentration first become a maximum? And either of these could be used as a signature of gelation. The question is, are these all the same? And if they are not, which is the one that coincides with what can be measured as the dynamic signature of gelation, right? So this is one of the questions we're interested here. So here is a couple of a few movies of our simulations. The green dots represent intra-chain interactions. The red dots represent interchain interactions. And you can see the interchain interactions are increasing with concentration. And since we can keep track of all interactions and how many stickers are sticking and how many chains are in a cluster and so on, we can calculate all the microscopic properties. So for instance, as shown in this movie over here, we can identify when does a system spanning cluster appear. And so by calculating the probability of finding a system spanning cluster for a number of different box sizes, we can identify the threshold at which the first system spanning cluster appears. So this you can see in our simulations appears around C over C star of roughly 0.35 or so. Okay. Similarly, we can also look at the probability distribution of chain size clusters, and it's usually recognized that when this becomes bimodal, that implies there's a likelihood of finding some really large or clusters with a large number of chains in it, and this is another signature of gelation. And we can also look at this point, and this turns out to be roughly around C over C star of 1 in our simulations. And finally, we can also plot the concentration of free chains, those with no interchain interactions, as a function of the number of chains in the system or the concentration. And we notice there's a distinct maxima, and that this maxima is another characterization of the gelation, static characterization of gelation, and this seems to occur at C over C star of 0.5. So what is clear is all these three static signatures are different from each other, and we are curious to know which one it can be identified with the dynamic signature, right? So let's now turn to our results with our dynamic simulation. So the first thing we've looked at is the end-to-end autocorrelation function. And we've fitted the decay at long times with a single exponential. And this allows us to estimate a relaxation time for the system as a whole, right? And you can see here that the behavior of homopolymers is very different from sticky polymers, that the relaxation as a function of concentration is quite different from for sticky polymers. Now, I want you to notice that we're using a sticker strength of epsilon st as around 5 kbt, so that's the depth of the well, and this is going to be relevant to my discussion later on, and this is the value we've used in all our simulations. Okay, so here are our first results. If you were to plot the relaxation time obtained from the end-to-end correlation function divided by the dilute limit, you notice that sticky polymers as well follow this very famous scaling law derived for semi-dilute polymer solutions, homopolymers, which is seen here for homopolymers, but only the onset of the scaling law seems to be happening at lower concentrations than for homopolymers. Now, here is a plot of the stress autocorrelation function for a few representative concentrations. And this one we have fit with a sum of exponentials because we want to be able to integrate this relaxation modulus that we're going to get out of this. And we're going to assume that the equilibrium relaxation modulus is 0 because it will be consistent with our belief that we are simulating a weak gel, right? So now, if you carry out the integration of the relaxation modulus over time, we can then plot the scaled zero shear rate viscosity. And you will observe that, firstly, it doesn't seem to diverge, but there is a distinct change in slope occurring at a unique concentration of C over C star. And that seems to coincide roughly with about 0.5, which is where we saw the free chain concentration becoming a maximum, right? Now, one can also do a Fourier transform and plot G prime and G double prime. And these are 4 plots at 4 different concentrations. Again, notice that nowhere does G prime or do G prime and G double prime become parallel to each other over any range of frequencies. They always seem to intersect. And this intersection point actually gives us an idea of a relaxation time. And G prime also levels off at high frequencies, which is known as the equilibrium modulus G naught. Right? So we can now plot this, the relaxation time obtained by the intersection of the two curves as a function of concentration, and similarly the equilibrium modulus G naught as a function of concentration. Curiously, we observe that similarly to the zero shear rate viscosity case, this also undergoes a sharp sharp change around the same concentration where we have the free chain concentration becoming a maxima. And interestingly, the slope of the relaxation time is similar to that of the zero shear rate viscosity, right? Now, if we plot the tan delta, it's clear that there is no range of frequencies at any concentration over which it becomes a constant. And similarly, and there is no concentration at which tan delta becomes independent of frequency. So these seem to be suggesting that we are actually simulating a weak gel, and we are definitely not seeing any signs of what is commonly observed for strong gels, right? So the fact that tan delta is decreasing with concentration tells you the system is becoming more elastic, but we certainly are not seeing the signatures that we see in the strong gel experiments. And finally, this is my last slide, plotting the zero shear at viscosity now, instead of versus C over C star, but versus concentration as a measure of distance from the gelation point, where we've assumed that the gel transition actually happens around zero point 0.6, which is the free chain concentration maxima. And we noticed that with increasing distance from in the post-gel regime, we seem to be getting a power law scaling of around 1.25, which in fact agrees with the prediction of Semenov and Rubinstein scaling theory for the post-gel regime. And also agrees with the experiments of Bromberg that I had shown you earlier on in the slides. Okay, so if I can conclude, essentially, it's not clear whether there is such a thing as a strong gel and a weak gel. Perhaps there is, and we think we can identify the difference with our simulations. We feel that the sticker strength of 5 kBt that we used has led to a weak gel, so we're currently carrying out simulations at a higher sticker strength to really examine if this leads to a strong gel. But what we have seen is that the dynamic signature, at least for the case of weak gels, seems to coincide with the existence of the free chain maxima. So with that, I'd like to thank you for your attention. Thank you.